So yesterday we solved that problem of how do we find the area under curve. But of course I was saying, well, that's just an application. We can use integration for other things. So let's just look at this idea of what we call a definite integral in a bit more detail, what they call the fundamental theorem of calculus. And that's very similar to what we saw at the end of yesterday as well, that we're saying, hey, the derivative of the primitive function is the same as saying the derivative of the integral of function t, and it turns out to be function x. So the equation of the curve is in fact the derivative of the primitive function. That's just all very formal, but do we need to know? But just some terminology while I'm there. Does anyone know, when we've written it like this with an integral symbol on that, what we call function t? Has anyone heard of that word before?
Integrand?
Yeah. So that's the integrand. The integral is the whole thing. Right, so when you put the integral symbol on that, that's the integral, but the thing we're integrating is the integrand. Look at me, giving you an English lesson here, right? The integrand. And then once you've got the answer, it's the primitive function. Yeah. All right, that's more important is how do we manipulate these things? Well, that's what I mentioned yesterday. For a polynomial, we just add 1 to the power of the power. That's our basic one that we looked at. And the order of the numbers, well, in this case they're letters, A and B, the same order on the answer. You can factorise. An integral symbol is a grouping symbol. So you can factorise out, but you can only factorise out constants. Because if you're going to integrate this with respect to x, remember that's what the dx stands for, with respect to x, then you can't pull the x out. So only pull constants out. This one's simply saying you integrate piece by piece. So if you have two things added or subtracted together, you can integrate the first one, that answer, minus integrate the second one, that answer, and so on. If for some insane reason, and I'm sure there's situations where we'd want to do this, if you want to find the integral from a to b, you could integrate from a to c and also integrate from c to b and get the same answer. And in fact, c does not have to be in the middle of a and b. C could be anywhere. But it would be true. The integral will always give you a positive answer if the function's positive. So if the function's positive, we know the answer will be positive. And it'll be negative if the function's negative. Now, the integral from a to b of function x, or f of x, will be less than g of x if, when we draw it, g of x is above function x. And that makes sense because we're talking about area underneath the curve. So if gx is higher than function x, then the area underneath it must be bigger than the area under function x. This one's really handy, I find. There's nothing that says the biggest number has to be on the top. It doesn't. You can swap them round if you want. But if you swap them round, you change the sign. Because think about what you're doing. If I was solving this one, I would have said, okay, I'll substitute in B, and then I'll take away when I substitute in A. So if I swap them around, I'm going to go, oh, substitute in A, but I'll take away what I get when I substitute in B. I'm obviously going to get the negative of the answer that I want. And there are good reasons for doing that, which we'll see as we go through this. If you notice symmetry, you can save yourself a lot of time. If it's an odd function, remember we're talking about the integral here, not the area. Then if I integrate from minus a to a, I know the answer has to be 0. Have a look at the cubic over there. That's a classic odd function there. If I was integrating from -1 to 0, I'm going to get a negative answer. It's below the axis. If I was to integrate from 0 to 1, I would get a positive answer. But by the symmetry, the actual areas would be the same. One's going to be negative, one's going to be positive, so they'll cancel out and give 0. So if you notice it's an odd function, again, you can save yourself some time. You don't need to worry about integrating. I know that's going to be 0. If it's an even function, the classic one over there is our parabola, then you could, instead of integrating from minus a to a, do it from 0 to a and just double the answer. Why would we want to do that? Well, because 0 is often a very easy number to substitute in. So at least you make one of the numbers easy to substitute in. Keep this in mind. When you're dealing with functions, we talked about this last year. If you have an odd function times an odd function, it'll be an even function. Odd times even is odd, even times even is even. Basically, if they're the same type of function, when you multiply them together, you'll get an even function. If they're different types of functions, when you multiply them together, you'll get an odd function. Okay, so integrate 6x squared. Well, I mean, okay, in reality, I'd probably just look at that and go 6 on 3. But theoretically, what I could do is I'll factorise the 6 out and then say integrate the x squared, x cubed on 3. Now I'll factorise the third out and I've got 2 out the front. As I say, the reality is I'd probably do it all in one step, but yeah, there's an example of, yes, you can factorise the constant out and get the right answer. Well, I've got to change it to index form. Cube root of x is 1/3. Be careful, because remember you're adding 1. A third plus 1 is 4/3, but then I'm going to divide by 4/3. Dividing by a fraction is the same as inverting and multiplying. So 4/3 must be multiplied by 3/4. And I just find that neater than writing a fraction with 4/3 on the bottom of the fraction. So, okay, well, I'll invert that fraction. Substitute in 5. Oh, that's not going to be an exact one, is it? We don't know the cube root of 5. We can't do that one. So I must end up with an irrational number, do I? In fact, I've even written it as, that looks like I'm saying x cubed times root x. It's not. It's x times the cube root of x. Because remember, you've got 4/3, 1 and a third. So we end up with 5 times the cube root of 5 minus, well, the other one's just 0. So there it is in all its glory. Now you might be looking at this saying, Mr. Simmons, you're an idiot. We don't know how to do trig yet. Until you remember the sine curve is an odd function. But hang on, I haven't got the sine curve. I've got sine to the power of 5. So, hang on. So sine to the power of 5. So I'm going sine times sine times sine times sine times sine. Well, sine times sine is odd times odd. That's now even. Times sine. So that's now even times odd. So that's now odd. Times sine. That's now odd times odd. So it's even. And finally times another sine. So it's now even times odd. We got an odd function. So, brilliant, odd function. Oh, the answer is 0. I tell you, if you remember that, especially once we do some of the extension 2 integrating, and all these trig integrals that we'll end up doing, you can waste so much time because you're in the habit, trig integral, I've got to go and integrate sine to the power of 5, and you spend all the time working out what the integral of sine to the power of 5 is, and you plug it in, you chuck the numbers in, you come up with the answer 0, and then you just start cursing because you realise, I was an odd function, I could have just said 0 and I would have got the answer. Now, here's an interesting one. Not that that's difficult to integrate. I mean, they're just polynomials. But notice we've got the minus 1 to 1. We've got the symmetry happening here. No, it's not an odd function. No, it's not an even function. It's going to be a mixture here because we've got odd powers and even powers. But remember, we can split the integral up. So I can rewrite it like that. Because if I just did the x cube's odd, that's going to be 0. May as well not be there. 2x squared, that's even. So now I'm going to have twice the 2x squared. X is odd. That's going to be 0. May as well not be there. 1 is even. So really, all I'm integrating is 2x squared plus 1. And I'll double it, go from 0 to 1. And there we go, 10/3. So if you notice things like that, you can take advantage of the symmetry. Pay attention to this one closely. Sketching what they call the signed area function. Really fancy for just saying we're going to draw the primitive function, okay? But the signed area function. So remember, our area function ends up being the integral from a to x of function t to t, which we know is going to be the primitive of function x minus the primitive of function a. So remember that. Here's a graph. Well, I guess it looks like it's a parabola, but anyway, of function x. How on earth, from that, can we draw a graph of the primitive function? Just to make life a little bit easier for this question, I'm going to assume that the area from 0 to a is the same as the area from a to b, is the same as the area from b to c, is the same as c to d. I mean, some is negative, some are positive, But I'm going to assume those areas are equal for the sake of this example. Okay. I like to draw my axes above it. So in my head, I'm thinking it's like a process. There's my function, underneath is the derivative. If I was to differentiate again, I'd put the second derivative and so on. So I put mine above. We know that the area at A is going to be 0. Now, why do I know that? Or am I just being told that? Have a look inside the box. Have a look inside the box. What's the integral? A to A. Right? So we're saying this area function, this is the difference between just drawing a primitive function when we're drawing the signed area function. The integral is going from A to X. Now A could be anything, and usually we make it 0 because it just makes life really easy. But for some insane reason, I've decided to make it here rather than make it 0, just to make life a little bit more difficult. Okay? But what I'm getting at then is at the point x equals a, the integral from a to a must be 0 because what are we saying? It's basically just a vertical line. There is no area to it. There's no width to this rectangle. So therefore I can plot that point. I know the answer to that question. Now, a will turn out to be a stationary point because its derivative is 0. Look, remember, this is the graph of the derivative. It's saying the derivative is 0. So I now also know that there is going to be a stationary point. Now, it might be a horizontal point of inflection, it might be a turning point, I don't know yet. We can investigate more. Okay, so area naught, I want to find the answer here. I'm now going to try and find the y-intercept or the a-intercept in this one. So this time I'd be going from a to 0. Remember I said I could swap the limits around? So it'll be the negative from 0 to a. So we said that those areas are all the same. I don't know the value. I'm just going to call it a constant a. But it's negative a. Because I'm not going from 0 to a, I'm going from a to 0. So I'll plot the the a-intercept at negative a. Okay. All right. Because I'm saying the value of this area is a. Therefore, the integral from 0 to a is capital A. But, remember what we're drawing? We're drawing the integral from a to x. So we're not drawing from 0 to a, we want from a to 0. So we'll swap the limits around, and that's why it would be negative a. It's really unusual. As I say, most of the times when we do these sorts of graphs, we start at 0 and it just solves any of these problems that we have. Okay? Now, why is B negative a? Because now there's the starting point. I know this area is a, but it's below the axis. So I now know that's negative a. Note, B, I now know is going to be a possible inflection point. Because the second derivative of that point is 0. Why second derivative? There's no mention of the second derivative. But look at your first derivative graph. At B, the first derivative is a stationary point. Therefore, its derivative is 0. Well, the derivative of the first derivative is the second derivative. So the second derivative is 0. We have a possible point of inflection. So I now know at this point at B, I have a possible point of inflection. Might not be. Let's see what happens with the rest of the points. But now to go from C, I'm adding on another area of A, still below the axis. So to go from A to C, I have twice A underneath. So it's going to be at negative 2A. Right. Notice C is also a stationary point, because once again its derivative at C is equal to 0. What about D then? From C to D, that's an area of A. So to go from A to D, I've got an area of A below, another area of A below, but then an area of A above. Add that all together, and we get an area of A below. So negative A. So I know that's going to be negative A. Okay, we've got some plots there. We're starting to get a feel for what this graph is doing. Remember how we said B is a possible point of inflection? certainly looks like that's what it's going to be, because how could it turn at B and go through both of these 2 points? Now, in the interval where I go from C off to infinity, because I'm assuming this curve's just going to keep going. So the curve must be increasing because the derivative is positive. This derivative graph, once I get past C, always has a positive value. We said when the derivative is positive, the curve is increasing. So the curve's increasing. There it is. But if you think about it logically, that looks like it's a quadratic. If I've differentiated something and got a quadratic, what must have I differentiated? And then we'll look at what? Oh, look, it's a cubic graph. Makes sense. So, but anyway, I think in the exercise there might be a couple of questions on that to have a go at, but we'll see how we go.